The following presentation was recorded at the 2012 SouthEast LinuxFest in Charlotte, North Carolina. It is licensed under a Creative Commons license. For more information about the SouthEast LinuxFest, visit www.southeastlinuxfest.org. The SouthEast LinuxFest would like to thank the following diamond sponsors in 2012 for helping make these videos possible.
Everybody, I'm here to talk about data warehousing, or everything that you never wanted to know about big databases, but were forced to find out anyway. So for a quick question, how many people here do manage a database or databases? So a fair amount. How many of you have more than a terabyte of data? Okay. More than 100 terabytes, anyone? There we go. So how much are we talking about?
790 terabytes.
Okay, that's pretty good. It's a lot of data. Okay, so I'm going to talk about a few things in this talk. This is sort of a general overview. I'm going to talk about some of the concepts of data warehousing, some general data warehousing techniques, and different database technologies that you can use for data warehousing. Because of the 1 hour time slot, I'm not going to talk about hardware, because that could easily be a whole hour in and of itself. And I'm not really going to go into analytics and reporting tools, because again, there's a lot of them out there and I just don't really have time to give a lot of coverage. But before I get started, I'm actually also on the core team in the PostgreSQL project, and I just did want to mention that version 9.2 is currently in beta, our next version, and among other features for the people who are doing large databases, we now support index-only scans, which has been a big deal on large databases. So anyway, that's happening now. But really, it's not what I came to talk about. What I came to talk about is a lot of people that I know have found themselves increasingly dealing with a lot more data than they ever expected to have. And they're sort of playing catch up in terms of figuring out what to do with this massive amount of data that they have. How to store it, how to retrieve it, how to get some sort of useful stuff out of it. And because of everybody doing this, we've got like this new buzzword, right? It's big data, right? Everybody's talking about big data. Everybody's got big data now. Got to get Hadoop because we've got big data, and we've got this and that sort of thing. And it's all new, right? And nobody ever had big data before now, right? It's only happened in the last 5 years. Well, not really. As a matter of fact, one of the various words associated with large databases is the term data warehousing. The term data warehousing was actually coined in 1970 by this guy, Bill Imam. And Bill came up with data warehousing and a lot of the sort of science and thinking behind how to handle large amounts of data that is still being implemented in solutions today. So the first thing that you should do if you suddenly find yourself in possession of terabytes of data is actually do some research. Starting with this presentation. And because there's already a lot of knowledge, there's already 40 years of knowledge out there about how to deal with data that is at the limits of what your computer can store and process. But let me get a little bit more specific here, because I specifically said this is data warehousing 101. So we say, what is a data warehouse? How am I using that term? What does it mean exactly? A lot of people think, well, data warehouse is big data. Yes and no. Because there's actually a couple of different kinds of large databases. And data warehouse, the term data warehouse does not apply to all of them. The term data warehouse, and what I'm going to be talking about, applies specifically to the kind of database system, the kind of data system, where you have some kind of processes, business processes, data collection, instruments, whatever, that are accumulating data, and that data is being sent into a storage location, and what the owner of the data wants to get out of it is some sort of knowledge about what's in the data. And one of the things about databases is that this accumulation process of data just keeps going on continuously, and the data just keeps getting bigger and bigger. And that's your data warehouse. That's why they use the term warehousing, because they're thinking about storage, the analogy from moving stuff. So But the term big data is used to apply to a couple of different things. Woo. Oh, that's very interesting. OK, my apologies. That happened in, since I opened this file. Big data refers to a couple of different things because part of it refers to things like I've been talking about, you've got the large data warehouse. The other way that people use big data to refer to is these databases like Amazon's transactional database for when you order stuff, or the Facebook database for all this stuff. And in their case, they're talking about a database that's designed to support thousands to millions of concurrent users, each of whom is doing very small units of work with the system. They're retrieving their personal profile. They're ordering one product, And that is a form of big data, but it is not a data warehouse. What I'm talking about for the data warehouse is you have large databases. Generally, your data gets in by batch imports. Generally, you're storing years of data. Your queries are often generated by large reports, so you generally have a very small number of users, but each user is using an enormous amount of resources, is combing through gigabytes, terabytes of data in order to find what they want. A better way you can summarize it, particularly since we're not having that layout problem, is your sort of transactional big data is big data for many concurrent requests for small amounts of data each. And your data warehouse is big data for low concurrency requests for very large amounts of data apiece. So we're talking about the second. Now, there are a lot of other terms used for data warehousing. So I'm going to go over some of those terms because they get talked about. And actually, I see these terms as basically sort of your subcategories of data warehousing. These get used a variety of ways. But think of this as your sort of three different types of data warehousing. The first one is archiving. And this has become increasingly popular later. The idea of the archive data warehouse is, let's put away all of our data somewhere in case we might need it someday. This has become increasingly popular lately thanks to government regulations that require retention of data for a certain period. For that reason, I often call this warn data, as in write once, read never. Because the business doesn't actually intend to do anything with the data. They are required to keep it by law. And they need to store it somewhere. And your main concern when constructing one of these archives is how to store it efficiently and inexpensively, not what you can get out of it or how quickly. Because you don't necessarily have any expectations of trying to get anything out of it at all. Your second type of data warehouse is what's known as data mining. And the way that data mining is starts like this. Gee, our web servers are generating a lot of data. I'm sure there's something useful about our customers in there, but I don't know what. And so then you start a data mining operation. And that's where you store a whole bunch of data, and it's a lot of data, terabytes to petabytes of data, because it's being generated by instruments that have a whole lot of data. It's often what's known as semi-structured data, as in you know certain things about the data, but there's other things that are just blobs. They're just text strings, binary things that you don't really know what's in them when you receive them. The data is generally produced as a side effect, almost always produces a side effect of something else. It's web logs, it's instrumentation, it's like one of these that I'm working on currently, this data mining, is telemetry for power generating windmills. And the main purpose of the telemetry is to warn you when the windmill's about to lock up or burn out. But now they're accumulating the data because they want to actually figure out some things about the windmills themselves from it. And because you generally don't know a lot about the structure of the data when you're receiving it in advance, in order to get useful information out of it, you have to do a lot of CPU-intensive processing. A lot of summarizing and searching for strings and mathematical comparisons and operations. So you have to do a lot of CPU-intensive processing. And for that reason, a lot of what you're optimizing in data mining, you're looking at a certain amount in storage, but one of your main goals in data mining is to have some platform where you can do a large amount of CPU intensive processing across as much of your resources as is possible to process your data. Our third type of data warehousing goes under a rather dismaying number of names. The three most common ones that get used are all acronyms, BI, DSS, and OLAP, which stand for Business Intelligence Decision Report Online, and the other one is Online Analytical Processing. It also goes under the non-acronym name Analytics. And what this really is all referring to is this sort of thing. Is you've got a bunch of data, you've got a bunch of business data, and you want to produce some nice charts and interactive visualizations of data in order to support management decisions about what you're going to do next. So generally, when you're building an analytics platform, you have data where the structure and the contents of the data are very well understood. There might be things like point of sale records or survey records or whatever, where you know you've got a set of fields or whatever, you know what kind of data is going to be in each field. Most of your data can be reduced to numbers, categories, geography, and taxonomy structures. And your primary concern when you get into one of these BI things is you're looking at a platform that allows you to do a lot of advanced and clever indexing, because that indexing is going to support having speedy visualizations that allow you to visualize and work with the data. So those are our three basic types of data warehousing. Now, one of the things that can make your life really complicated is in a real-world situation, you're frequently trying to implement more than one type at once. Sometimes you're trying to implement all three at once. And sometimes that means adopting a hybrid solution. In some businesses I work with, that's actually meant having more than one data warehouse for the same essential body of data. One in which they're doing the regulatory archiving and storing 10 years of data, another one in which they're only storing 1 year of data, but they're mining it, and then another one where they're taking all of the mined data that is now highly structured and putting it in an analytics platform. But those are three sort of basic activities. So let me get some other terminology out of the way. Again, going back to Bill, going back to 1970 and that sort of thing, because this stuff still applies even if you're using some sort of modern search-based non-relational platform. One of those is dimension. You know what? Could I ask you a favor in this check shirt there? Could you give me a glass of water? Sure. Thanks. One of those is dimension. And you get this thing called dimension. And I've seen this term misapplied a lot to a lot of different sorts of things that are not dimensions. So let me explain basically what a dimension is. In a lot of data warehouses essentially have one gigantic table or database or population of files. And this one gigantic table is known as a fact table. That is your actual data that you're interested in investigating. Now, this data can be summarized and understood in different ways. Like, for example, you often have various categories. Like say we're dealing with sales data and you've got it organized by customer. So you've got your customer idea. What's even more useful and much more of a dimension is you might have something like a taxonomy, a whole hierarchy of categories. Category, subcategory, detail category, that sort of thing that eventually point to the specific category in the fact table. Or you might have something else that helps you visualize the data, like geographic information, which is wonderful, useful dimension. And it refers to information that comes from outside the database, which is the geography of the world. But it's still stuff that you want to know. What were my sales like? How many hits did I get from Australia? So these are your dimensions. These sort of canonical data, information that doesn't change very much, versus the main data that's actually coming in. Some more examples of dimensions, localization, region, product categorization, URLs, transaction types, account hierarchy, IP addresses. This is what I work with a lot in the Mozilla stuff, OS version build. And in a well-formed data warehouse, dimensions are often going to be structured hierarchically, you know, like this, like OS version build, for example. Because then you can summarize by OS, you can summarize by OS and version, you can summarize by build. There's some synonyms for the word dimension, particularly for newer technologies. One of the ones that shows up in the Lucene-based stuff that I'll discuss later is facet. You hear a lot, and that basically means dimension. Taxonomy, for all those category trees. For systems that have index-organized data, you'll often hear dimensions referred to as secondary indexes, or sometimes as views. Now, those last two are confusing because those terms are also used to mean other things that are not dimensions, other bits of database technology. So one of the difficult things in comprehending the data warehousing world is that the same terms are used to mean different things depending on which vendor, which open source project, which domain of data warehousing you're talking to. Another term that actually I want to talk about, because it comes up and because it's important in data warehouse design, is this term called, is another common term you'll run across. So one of the common things that you'll have in a very simple data warehouse, which actually is numerically very common, you know, you have, like, say, your web logs. So your purpose of your data warehouse is to mine your web logs. You have your web logs, and that is your fact table. It's this gigantic series of digested web logs. And then that has various dimensions, our taxonomies and geographic dimensions and that sort of thing around that. And the term for this used in the data warehousing world is, it's called a star schema, because this thing sort of forms a star, you know, with the fact table at the center. And when I explain systems later on, you'll understand what this important distinction. Now, there is a different kind of data warehouse that's a little bit more complex, because for some highly structured data, for some large business operations and stuff, you'll actually have more than one fact table. You know, so like this might be purchases, and this might be inventory movement, and this might be, you know, for like an ERP system, right? And this might be orders, you know, and these are all obviously closely related, but they're not the same thing. They're different fact tables. Or if you're doing analysis of, like we're doing analysis of, you know, windmills and that sort of thing. This might be weather conditions, which we record, you know, by minute, and this might be windmill behavior, and this might be maintenance activities. So again, related stuff, but each one of them forming an enormous separate fact table, which then relate to different dimensions within the database. And this more complex kind of data warehouse is what's known as a snowflake schema. And you can sort of see this, the snowflake pattern, right? Because it doesn't have a single fact table in the center. It has more of a ring of them. So that's the snowflake schema. So if you hear those terms being used in the future, you'll know what star schema and snowflake schema are referring to, because I'm going to use them later in this presentation. So here's another term. This is what started this presentation, because I went into a client where they were about to do something with 20 terabytes of data. And I said, okay, so let's take a look at your ETL processes. And they're like, what's ETL? And I was extract, transform, I'll tell you this, what's ETL? And the thing is, it was startling to me because the entire purpose of this company was to deal with terabytes of data. It wasn't something they were doing as a side effect. This was their business, and they hadn't heard this term before. And ETL stands for extract, transform, load. And simply put, this is how you get your data from wherever it comes from into whatever your database solution is. Preferably somewhat cleaned up. So, you could be going from, say, a whole bunch of web logs to a web analytics DB, a whole bunch of point of sale files to a financial reporting database. You could be going from your transaction processing database server, which can be emitting changes and going direct into 10 years of data history. It's also occasionally called by data warehousing geeks ELT, because of the popularity of, if you have a relational or clustered database system, of doing your transformations inside the database. So what you do is extract, load, transform, instead of extract, transform, load. But they basically mean the same thing. It's how do we get data from here to there. So you want to get it from your source. You want to clean up a bunch of garbage in the data, because any large volume of data, you're going to have a bunch of garbage, right? You want to identify attributes and dimensions and mark them somehow, depending on your database system. Like if it's going to a relational database system, you want to separate out attributes, put them in fields. You want to separate out the dimensions and put them into lookup tables. You want to deduplicate duplicate information, because if you haven't looked for duplicate information in your database, I guarantee you that you have some. And you want to possibly calculate materialized views and update indexes, depending on your design. And so you do all that. Fortunately, there's a lot of good tools to help you with this. I mean, I have the, such as, I mean, for example, these are three of the top ones. So there's Talend, which is an independent open source, yeah?
Can you make this like this?
Yeah.
I thought the star schema actually does the duplication, isn't it? If you're trying to do
The schema is not going to do anything for you. Code has to do something.
you're bringing in all the data. And
Yeah.
sometimes, that's going to result.
And sometimes it'll have duplicates, and you need to do something. Now, if you're using a relational database, it'll give you an error if it encounters a duplicate. But then you have to do something when you receive that error. The database is not going to do anything other than error out and refuse to accept the data. And that's not generally a satisfactory solution for any data warehouse.
Could you get the aggregation and deduplication?
Yes, but that's part of the ELT. That's part of the ETL. That's something you want to do as part of the ETL. You don't want to store highly duplicate data full of garbage as your main referential data warehouse, because then every time you make a request of that data warehouse, it requires a whole bunch of extra processing that you should have done when you imported the data in the first place.
So some amount of duplication is okay.
It's a question of, it's a decision of how much time do you want to spend when you're importing the data versus how much time do you want to spend when you're trying to get stuff out of the data. So for some of the ETL tools, Talend, independent open source, Java-based thing. Kettle was an independent project, got taken over by Pentaho, and it's now part of the Pentaho suite. In Informatica is an example of an old school commercial, basically ETL platform. They call it data lifetime management, but it's basically just, it's ETL++. And then they give you these nice sort of graphical things that allow you to do sort of formulas and diagrams and that sort of thing of, this is where my data is going from here to there, and apply this operation and insert it into this other thing. I think this is a Talend screen. Yeah. But this is still the most popular method of ETL. And most of the sites that I run across in most of the places, even very large enterprises, most ETL takes the form of ad hoc Perl, Python, Java scripts, even shell scripts that do various transformations of data. A few tips on doing ETL. Always think about the volume that you're dealing with. So every operation that you do should be thought of in terms of bulk processing or parallel processing. You should never be thinking in terms of a single row or a single document. Because if you iterating over a single document works fine when you're testing it. When you have a billion documents coming in a day or an hour, it doesn't really work. Software gets much more efficient when you can actually do things in batches. The other thing is, you should think of terms that inserting into permanent storage, inserting into your long-term data warehouse should be the very last step of your transformation. Now, in relational databases, that often means you can insert into a bunch of temporary tables and then do transformations of those temporary tables and then insert them in the final fact table. In a non-relational, operation, you might have a separate server that handles the partly digested data, and then you insert it into your final server. No updates. Now, one of the things that actually has changed relatively recently in how to handle ETL on a lot of the sites that I work with is that we've started to move over to using queuing software for handling a lot of the incoming data, because it allows us to do continuous processing of incoming data rather than doing it in, say, staggered hourly batches, and allows us to keep up with a lot more of the demand now for users wanting to actually see analytics from data that was generated only a few minutes ago. So the other big thing is a lot of the questions that people say, yeah?
I just had a question on no updates.
Yeah?
With no updates, does that include like type 2 dimensions, slow change dimensions, where you have information at the stored point in time? Because you would have to expire that record to keep that going, so that would be an update.
Oh, you mean for, yeah, so state information and that sort of thing? Yeah, those are challenging for that reason. I haven't seen a really satisfactory solution for those because you're either doing, so he's talking about time-based databases. We have records that represent a point in time for a particular entity. And so the point in time has to be terminated at some point, and the termination basically means doing an update to a record or a document, which is really expensive when you think about doing it to millions of them. And I haven't actually seen what I ever felt was a really elegant solution to that problem. Because the alternative is to keep the beginning and end information somewhere else, so you can do it append only. But then the cost of calculating which records are current of a particular point of time goes up tremendously. So, you know, it ends up being awkward on one end or the other. So, a lot of people ask, what kind of database should I use for this? Here's the other reason why I wanted to give this talk, is that the other thing that I encounter a lot is that people have heard of one particular database that handles big data. And therefore, they are convinced that they have to use, if they have a lot of data, they have to use that particular data system. And sometimes that's fine, but sometimes that system is really inappropriate for what they want to use it for, and they go through a lot of pain. So I want to actually go over a survey of the different types of data warehousing systems, data warehousing database systems there are, and what they're good for and bad for in general. So here's our 5 types. One is your standard relational databases. The second is MPP, relational databases. We'll explain what that means in a minute. The third is column store databases. Fourth is MapReduce supporting systems. And the fifth is enterprise search. And these are actually in kind of a rough chronological order in the order of which they were invented. So our first thing is standard relational databases. And so here I'm talking about PostgreSQL, MySQL, Oracle, SQL Server, that sort of thing. And the nice thing about standard relational databases is they're kind of designed to do everything. They don't necessarily do everything well, but they do everything. So they become actually sort of an all-purpose solution if your data is not particularly large. And these days, given the speed of hardware, not particularly large tends to be more in the realm of a couple of terabytes. You know, so it's, you know, they sort of are adequate to all tasks. They're easy to use. They have low resource requirements. They're well supported by all kinds of different software. They're very familiar. You know, it's just that you don't necessarily want to throw your 790 gigabytes on Postgres or MySQL because it's not really going to handle it well. I mean, actually, this is a wildly oversimplified sizing chart, but it gives you an idea of what I'm talking about. So, like, you know, you've got half a terabyte. Sticking it in MySQL is fine. Postgres is, depending on your use case, maybe good for up to about 8 terabytes, you know, or so. But you know, once you start getting north of a few terabytes, once you start getting in like the 5 terabyte range, it's time to start thinking with current hardware. It's time to start thinking about using a data system that is specifically designed for large data. One of the ones that I'm going to talk about. So, speaking of data systems that are designed for large data, let's talk about our first one historically, which is MPP. Another acronym. MPP stands for Massively Parallel Processing. Horrible marketing term, but it stuck. And what this specifically refers to is, these are basically relational databases, but the query engines are designed not just to execute queries across, on a single processor, across multiple processors on a machine, but in fact across multiple machines. This is actually one of our marketing query diagrams from Greenplum, back from when I worked at Greenplum. You know, and they're talking about this is that what happens is parts of the query get executed on each server, and then the different servers exchange data between each other. And there's actually a bunch of solutions for this because it is the oldest type. For example, Teradata, Greenplum, Netezza, DB2 has a parallel processing edition that is basically an MPP database. And you know, and there's a couple of others that are not represented here, and I'm not really remember what they are, but you get the idea. So Now, what MPP is generally good for is they're good for that CPU-intensive data mining, among other things. They support complex query logic. They support custom functions and complex calculations. They support reasonably sized data. I mean, my general experience is when you start to have problems with them is somewhere in the hundreds of terabytes, depending on how much you're willing to spend on hardware. Generally, people actually tend to use MPP systems these days on smaller systems for cost reasons, because the thing is that all of the production quality MPP systems I know of are proprietary, and they all have fairly expensive licensing. You know, on the order of like, I think Greenplum licenses there by the terabyte, and they're like $10,000 or $15,000 per terabyte, which really tends to add up. But you know, for your sort of data mining operations, they can be really excellent, particularly if you have a mining staff who are familiar or who use tools that are designed for relational databases. Also, the other thing is, because they're the oldest types, a lot of the vendors who do these, like Greenplum, like Astrodata, have been hybridizing them with some of the types we see later on, adding features from some of the other types of the data warehouses so you can get some of the functionality of both. Other types of data warehouses, including column stores. So a lot of people ask, you know, what's a column store? You hear these referred to sometimes. It would be sort of simply is that it's this sort of 90-degree pivot where you take a relational database, again, and you take everything, you take like this is your standard relational database is known as what's a row store. So data is stored in rows, you know, and then groups of rows go on a data page and they get stored in a table and that sort of thing. And that means that anytime you're querying a row, anytime you're looking for an entire row, that's a relatively fast operation. The problem is that what if you want only one column over millions of rows or billions of rows? You have to actually read the whole rest of the row for all of those rows. I mean, sometimes you can get it from an index or something like that. But if we're going to the heap, you have to actually read every row. So you've got, like, say, you know, what they did for column stores, and this was introduced in 2000, was they turned that 90 degrees. And so the data is actually stored in columns, and the database maintains pointers as to which of those columns go together as a row. And that means that any time you're looking up an individual column, it's very fast because those records are all because that information is all contiguous. But if you have to actually join a lot of rows together, it's slow because that information is not contiguous. So, you know, it's the sort of inverse, right? It's imagine if you're used to indexes and tables in a relational database, it's like your indexes became your data and your data became your indexes. There's a number of tools for these. Vertica was the first commercialized one, and people often consider it the most production quality one. Parexel, InfoBright is a MySQL table type column store. LucidDB, independent column store database, pretty good. MonetDB, I don't know anything about it, but it is a column store. So column stores are good for aggregations and transformations of highly structured data. Because everything has to be organized into columns, and the data in the columns has to be remarkably similar to each other. And for column stores to really win, they do things like run length compression on the values, which means that you have to have sort of a defined range of values. So that makes them really good for business intelligence, analytics, graphing, that sort of thing. It makes them not very good for data mining. Now, column stores, if you have highly structured data, column stores can also be good for archiving because pretty much all of the serious column stores have compression built in. And so that saves you on storage. Even if it has a lot of features you don't really need for that. Also, they're very slow to write to because of the reorganization of the data that takes place when you insert new data. And frequently updating existing data or deleting data is actually impossible. You have to take the existing data and rebuild it into a new table and then delete the previous table. So imagine it's fairly expensive. So one other thing came to us in roughly 2000, although it was a while before it showed any real use in the field, and that was this technique called MapReduce, which you hear about a lot. MapReduce is basically, it's an idea, it's a technique, it's sort of an algorithm for doing distributed processing of any kind, really. Where you do functional programming, and you divide all of your functions into a map section and a reduce section. And so you use the map to gather all of your data and the reduce section to actually process the data and move it on to the next stage. And this is generally best done within a MapReduce framework, a tool that actually supports running MapReduce code across a large number of servers. The most popular, overwhelmingly the most popular of these is Hadoop. People use Hadoop to the point where Hadoop is really sort of your open source solution for MapReduce. CouchDB actually does have some support for MapReduce operations. It's not really suitable for data warehousing because they have limitations and they're not very good at storing large amounts of data, but for fairly small amounts of highly unstructured data, it can be useful. Aster is a hybrid MapReduce MapReduce relational database based on Postgres, as is one I forgot to put on here, which is called Hadapt, which is a hybrid MapReduce relational database. Now, this is an example, one of your textbook examples, a very simple MapReduce algorithm that basically just says, if we meet this criteria, then go ahead and emit the value and return it to the function key. One of the big problems with MapReduce as compared to some of the earlier types we looked at, like MPP, which is actually sort of your main contrast, because both of these are very good for data mining, is that it's basically taking something that the system used to do for you and putting it on you as the programmer to develop the algorithm for how to find the data. And that's both a disadvantage and an advantage. It's an advantage in that you're not limited to thoughts of standard relational or tabular data. You can run MapReduce systems over libraries of images. You can run MapReduce systems over bioinformatics. You can do any kind of processing that you can write as code can be reduced to a MapReduce algorithm. The disadvantage is that your requests to the MapReduce system tend to get really complicated and tend to be a lot of code and a lot of maintenance, and you have to hire very smart people to write them for you. MapReduce is not a point-and-click operation. So your sort of contrast here is MapReduce versus MPP. Now, tremendous advantage, open source, there's a lot of open source and free implementations, and therefore that drives your cost way down. Also, you can there's no theoretical limit on the amount of data that you could pump into a MapReduce system, and so that tends to go into the petabyte department here. But on the other hand, you can writing routines by hand as opposed to using an advanced query planner. You are the query planner in a MapReduce routine. MapReduce tends to be very resource inefficient in terms of the amount of resources required to do the same amount of work. But it's a generic solution as opposed to a specific sort of relational database solution. Also, the nice thing about it is, because it is inefficient and highly distributed, you can use cheap software, cloud hosting, and that sort of thing, whereas you can't really do that with an MPP platform that's really expecting good, very consistent hardware. So there's this, this sort of decision making to go through and deciding which option makes more sense for, say, a data mining, which both types of data warehouses are very good at. So this has been, enterprise search is our most recent entrant into the data warehousing arena. And enterprise search actually started out with what it sounds like with search engines, specifically with the Lucene project. And what people realized was that they didn't have to use Lucene just to do search on their live website. You could actually store a large amount of text on your servers and use Lucene to do search internally. And so a couple of different forked projects, I decided to do this in different ways. One is the Apache Solr, the other one is Elasticsearch. And they've added a whole bunch of features to these, to the point where they are effectively data warehousing databases, and they can actually solve some of the same problems you would have solved with other types of databases, particularly cases that are oriented towards locating and filtering small amounts of data from a very large data population. So where it really wins is you have a large amount of data, most of which you know very little about the structure. So it might be memos, it might be web pages, it might be HTML documents, it might be JSON documents, whatever, you know. So you know very little about what's actually in them, and you need to find things in. So, and you can do both sort of lightweight data mining and support BI and analytics systems. They also have an interesting thing that is regarded as either a feature or a misfeature, depending on what you want, which is the ability to return approximate results in order to return results faster. And of course, they come built in with a lot of special features for web-based data. So in a lot of ways, if you're sort of looking at this, you say, you know, your sort of division is you might be looking at Elasticsearch versus column store as a contrast in those things. Because particularly this was actually where I was specifically looking at it in one project. Because of the support for what they added to enterprise search, both in Solr and Elasticsearch, is support for this thing called faceting. And faceting are materialized indexes, and you can use the materialized indexes to do basically column level information out of your data. So you have to update both of them by batch load. Enterprise search is better for semi-structured data. CStore is better for fully normalized data. So far, all the search implementations have been uncompressed. That could be changed. Generally with this, you know, if you need to scale it massively, for like Elasticsearch, you're going to do sharding. For column store, you're going to do parallel query, approximate results, exact results. Now, there's still some stuff to be implemented in enterprise search to really make it sort of data warehousing, more of a data warehousing contender than it is now. For example, you can really only do, I said this was going to come up again, you can really only do a star schema. You only have one table in any kind of enterprise search implementation. It doesn't have the concept of having different divisions among your data. And currently, for both Elasticsearch and Solr, you can't combine indexes, and it doesn't really have any concept of data aggregation. So if you really want to do full-on BI stuff, you have to use enterprise search to generate your data and then feed it to another system, such as a relational database or MapReduce system, in order to do your aggregation for you to represent the analytics. But, you know, for people who have really massive amounts of data, it can be worth going to that work, because one of the things that the column stores don't really, that none of the existing column stores really have, is any support for having large-scale clustered databases. So for really efficient column store operation, you're limited to what you can put on a single server. So a few other concepts that I want to go over. Let's see. We've got about 15 minutes left. So I'm going to actually breeze through these so that we'll still have some time for questions, because I got over the main things I wanted to cover. Some of the other things. So I work in the relational database world. I work specifically on Postgres. And I wanted to actually address a couple of other things that are really useful in data warehousing that people frequently don't know about at all. One of those is windowing queries. How many people here know what a windowing query is? Yeah, see, and one other person who's not raising his hand in the back. Because I know he knows about windowing queries. So one of the things, because this is actually a concept that could translate to non-relational databases, it just hasn't yet. So the idea of a conventional aggregate is you have your bulk data here, and you can condense it down to a handful, you know, of this. So like these are, say, the sums of a bunch of values, right? So we're running the sum, and we do that. The idea of a windowing query is that instead of just condensing the aggregate is you can get back both the values, and you can run aggregate operations over a window of the other data. And this way you can say, for example, compare the value for an individual row to the aggregate value. So say, for example, I want to see all of the rows that are more than 10% above the average for the set. That's an operation you're doing all the time in analytics, that sort of thing. I want to see everybody who's in the top 10% for the set. That's the sort of operation you're doing all the time, and that requires a windowing operation. Now, SQL has a whole syntax for windowing operations. So say, for example, we had this event table. This is a good example. This could be machines turning on and off. This could be, I actually did this basically for database connections. where you have an event, you got some surrogate key for the event, and you have a type of event, and then you have a start of the event, and you have how long the event went on, right? And what I want to know is, say, for example, at what second were the most concurrent events going on, and how many events were they? And so then you can actually do a sort of pile up here where you stretch out your series of events into a group of ones and negative ones. And then everything adds 1 as it starts and subtracts 1 as it ends. And then you get your windowing phrase up here where it says order by the start and then select a sum. And then I want to actually know the maximum concurrent ones. You can look at this later. This is actually on, this presentation is online. You can look at it later. But that's the basic idea. And a lot of the concept here is, in SQL, is it takes the concept of stream processing. For people know SED, the command line utility and that sort of thing. It takes the process of stream processing to SQL. And it turns out when you're dealing with really large volumes of data, stream processing is a very powerful concept. Because writing a bunch of data, then retrieving it and doing an operation to it, and then writing it again, and then retrieving it and doing another operation to it again is really inefficient. It would be much better to pump the data through a process and do all of the different things you needed to do to it in series before writing it. And within the SQL world, windowing queries can actually give you that and allow you to replace literally pages of application code in a lot of cases. One of the examples that I have on a blog or something is where I actually did the rankings for an entire fantasy football league using a single windowing query. So now another concept, and this one does translate to both relational and non-relational databases, materialized views. Something you should actually understand. And the basic idea of materialized views is query your results as a table. That is, I'm going to take the results of a query request and store it and put it on storage, so that when I want to run that request in the future, I can get the answers back a lot faster. And where this really works is where the underlying query is going to be expensive, either because it accesses a whole lot of data or because it does a whole lot of calculation. And where it's going to be frequently referenced, where you're going to want that information a lot. Now, you're not necessarily going to build a material query, a materialized view, as exactly the query that you want for the end user. Often it'll be sort of part of it. You know, it'll be something that was going to be in the from and where clauses, or something that's a pre-processing thing, like right before you run the group by, you know, and that sort of thing. And you might manually or automatically update it. It really depends on the product and what sort of support that you have for the materialized views. But that's the essential concept. And there's a lot of tooling that goes with materialized views, but the central concept is I'm going to take a query or part of a query I was going to run anyway, and run it ahead of time and store the results somewhere permanent so that I don't have to do that at user request time. Now, this also translates into non-relational databases. A couple of examples here. CouchDB has this concept of views. And basically what you do is you run a MapReduce operation in CouchDB, which is expensive, and then you store that MapReduce operation as a view. And that's actually updated at request time, which I had some issues with, but we'll talk about that later. It's updated at request time, but it's actually stored as a separate structure within the CouchDB database, so that if you need to run that MapReduce operation again, you can get the answers back a lot faster, rather than having to wait for them. For that matter, like I said, the enterprise search things have this concept called facets. And the facets are currently, they need a lot of expansion to make them actually a lot more useful, but the facets currently basically, you can form a request for certain data and then store that as a facet. And then when you need to actually run that as part of your search again, you can get it back from the facet. And these get updated at data change time. So now, regardless of relational and non-relational, for really large databases, there are different ways that you can update them. The best way to do it is, if you have some form of batch load process or stream load process, is that you want to update the mat views as the data comes in. That is the most efficient way to deal with it, pretty much regardless of that. Now, in some cases, that's not practical to do, and you have to do something like updated according to a clock or calendar. So you have a time-based table, you might update it every hour, you know, in batch, and then create a mat view. There are some systems where it actually checks the mat view for updates when you run a data request, like CouchDB, and then updates it when you run a data request. That tends to not be such a good idea, because the thing is that in a really large database, those data requests take a really long time to run. And so you don't want a user waiting for them dynamically, right? The worst for any really large database is to have a trigger or some analogous concept that automatically executes when certain things are updated. Because it's almost certain that any time you need to update some part of the mat view based on data changing, you're going to need to update millions of rows in the mat view, or maybe rebuild the entire mat view. And low-level automatically triggered functionality in the database, like an SQL trigger, does not have the discretion. It does stuff row at a time, and row at a time, anytime you have a billion rows, is a bad idea. Other tips for mat views: mat views should be small, a tenth to a quarter of RAM, you know, at most. If your mat views are much larger than that, on each node, if your mat views are much larger than that, then you're not really, then you're basically going to be reading them from disk anyway. There's some cases, I mean, when your data is really huge, you know, like you're dealing with a petabyte of data, then a mat view that's 100, you know, that's a mat view that's 200 gigabytes is actually seriously advantageous. But if you're getting in the circumstance where the mat view is a quarter the size of the raw data you're making the mat view over, then you've done something wrong, usually. Mat views in general should support several different query types, or one really important one. Also, looking at mat views like the base tables, look at ways that you can append and truncate, not update the mat views. Because again, you have to think about, you're going to be doing these operations over millions or billions of rows or documents. And so you never want to do that on a search and replace algorithm, because those are always really slow. And then also, if you're dealing with a system that supports indexes, of course you want to index the mat view like crazy, unless you're dealing with a system where the mat view basically is the index, like enterprise search. So briefly, we're running out of time. I'm going to go with briefly, another term you might hear is OLAP, because I brought it up before, online analytical processing. This was invented by a company that was acquired by Microsoft in the mid-90s. At least as far as I know, they invented it. They're the first ones to commercialize it. And the idea of OLAP is, there's this concept in OLAP called cubes, which is not strictly accurate. The idea of the cubes is, remember I talked about the concept of dimensions, right? The idea is that you actually take your dimensions for your data and you create a multi-dimensional virtual space where each of those dimensions is a spatial dimension. And then you can navigate around it. You can zoom in and out, and you can navigate around the different aspects of the dimensions and sort of drill down into different things. This is output from Mondrian, which is the main open source OLAP tool. You know, drilling down to sort of different portions of your sort of aspects of your data. It's a visualization technique. It tends to be CPU and particularly very RAM intensive. For one thing, I've yet to see an OLAP engine that could handle spilling to disk. And so you tend to, on really large OLAP databases, you tend to find yourself maxing out your budget for RAM. It works really well together with column stores because it's a lot of the same sort of structural information. So we got a few minutes for questions. This is my contact information. Oh, by the way, don't forget, Postgres 9.2 in beta currently. So, questions? Somebody must have some questions. Yeah.
Yeah, I kind of wonder about, so ETL from documents that are just sort of generated makes sense, right? You know, there's new documents, governance,
Yeah.
simple. But what are some complexities around when your source is an online transactional database? And, you know, we've got online transactional databases that say they don't have modify times in all the rows. So, like, how do we know?
Right. Well, I mean, if data doesn't exist, you're not going to get it through the ETL. But even when you're going from, to repeat the question, yeah. So his question was, he understands ETL when you're coming from sort of raw data form like, you know, Word documents or whatever. But he's saying, what sort of transformation do you need to do when it's coming from another database system where it's already presumably normalized? Well, the second thing is, The other thing is that the database structure that you're using, the schema, the structure of the tables, the indexes, that sort of thing, for transaction processing is frequently different than the one you want for the same data when you are mining it or doing analytics over it. At the very least, you're going to want a different set of indexes. Frequently, you want different table structures. Sometimes you're going to use a different database system for the warehouses you're using for the transaction processing. And so there's going to need to be some work done, some transformation to get the data from one part to another. And also you might be updating a bunch of mat views and indexes and doing other cleanup and that sort of thing. So other questions? You've got 800 terabytes of data. Surely you must have questions.
A lot of them are proprietary, I can't say.
Oh.
I will say though that many questions we have just surround how to deal with it, because that's stored in the Postgres 8.2 database, by the way.
Really?
Yes.
That's very impressive.
That's what I said when I hired on. What?
It's not one Postgres 82 database.
No, it's split across multiple shards.
Yeah.
So
The first thing you want to do is, like, say, ring up the Aster data folks and see if they can somehow graft Aster on top of existing Postgres databases. That'd be my first thought, honestly. Because you really need something on top of all of those databases that allows you to pull data from all of them. And nothing in vanilla mainstream Postgres is going to allow you to handle that situation easily.
I didn't mind that as a try.
Yeah. Plus the other problem, by the way, that I didn't mention earlier to this is here's the other thing that becomes a really painful reality when you start dealing with really large volumes of data, which is the inability to do upgrades of any kind. Because you simply can't, any kind of upgrading that requires a data rewrite is just completely out of the question. And particularly this for Postgres 8.2 is to get anywhere beyond 8.2, you have to rewrite all of the data because we changed the file format in 8.3. So so you're basically not upgrading, and I wouldn't talk to you about upgrading. And you run into that with other things. For example, I worked on Greenplum for a while. With Greenplum, we had to really work on not making a lot of changes to any change in the file format and that sort of thing. So we have time for one more question. If anybody else has another question. No? Okay. So we'll actually finish on time here. So thank you very much.
When we created Asterisk over a decade ago, we could not have imagined that Asterisk would not only become the most widely adopted open source communication software on the planet, but that it would impact the entire industry in the way that it has. Today, Asterisk has found its way into more than 170 countries and virtually every Fortune 1000 company.
The success of Asterisk has enabled a transition of power from the hands of the traditional proprietary phone vendors into the hands of the users and administrators of phone systems. Using this power, our customers have created all sorts of business-changing applications, from small office phone systems to mission-critical call centers to international carrier networks. In fact, there's even an entire country whose communications infrastructure runs on Asterisk.
Digium has always been about creating technology that expands communications capabilities in ways that we could never have imagined. And that's part of what's game-changing about Digium. Today, we're doing it again, this time by introducing a new family of HD IP phones that extends control of the user all the way to the desktop.
The launch of these new products represents the next phase in Digium's history of innovation. These are the first and only IP phones designed to fully leverage the power of Asterisk. When we first discussed our expectations for building a family of phones for use with Asterisk, our requirements were pretty simple. We asked the team to build the phones such that they were easy to install, integrate, provision, and use. I think you'll soon agree our engineers have delivered on that goal. User feedback is validating that when it comes to operation with Asterisk-based systems, including our own SwitchVox-based product, these are the easiest to use, best integrated, most interoperable products on the market today. The Digium family of phones will initially include 3 IP desk phones, uniquely designed to complement any Asterisk or Switchvox-based solution. These phones are different for a number of reasons. First, they're exclusively designed for use with Asterisk. Secondly, we've made it really easy to auto-discover and provision the phones. Next, we've made it easy for the phones to access information inside of Asterisk, allowing tight coupling between an application and the phone. Additionally, we've created an applications engine that allows users and developers to create and run their own apps on the phone. And finally, we've done all of this at a very compelling price point. At Digium, we're always thinking of ways to give our customers the best value in business phone systems and also give them the power to create their own solutions for any communications challenge.
We'll continue to push the boundaries, not only to make Asterisk cooler, faster, and more technologically feature-rich, but to make Asterisk and VoIP communications even easier.
And together, we'll change the way the world communicates.
Again.
Cloud stacks are everywhere.
This is the way to better utilize all your resources, and it makes managing all your resources pretty easy.
All of the innovation is happening in open source.
The collaborative nature and of the community and the speed at which these deficiencies, these bugs are getting discovered and fixed is a thing that really shows the power of the open source community.
It is global, and it's definitely because of the users.
Community people are extremely friendly and always ready to help.
If you go onto IRC any day, you'll see these guys helping each other out, and they're all doing it like in a selfless manner.
The product is transparent for everyone. Everyone can look at the code base. Everyone can see how Cloud Stack is being built. Nothing is proprietary. Everything is open.
In many ways, it's absolutely vital to the ongoing health of Cloud Stack.
The most exciting event in recent memory for me was our first developer boot camp. And our call gave people, I think, maybe 2 weeks notice to come attend. I was expecting 25 or 30 people. So we ended up with 87 people and had to go get more chairs into the room twice.
Everything within cloud computing is commodity and is open source. And so I don't think that you'll see anywhere where open source is not pervasive in cloud computing. And so I think it's an assumption. I think when you talk about cloud computing, you're really talking about open source cloud computing.
CloudStack is a robust solution for large deployments.
You have dozens of data centers and thousands of servers in each data center. These hardware is going to fail, and CloudStack is designed to handle, number one, that mass scale. Number two, it's designed to handle the failure that inevitably happens in large deployments.
We started working on CloudStack over 4 years ago, and it was the original set of people working on it. Had a background of delivering software to telcos and service providers.
Lots of QA, lots of users actually using it.
High availability is the key feature. Multiple hypervisor support, different network models. You can pick up whatever suits you better.
Cloud Stack Management Server can be deployed in different physical machines.
It definitely has a huge footprint. It's being deployed everywhere.
There's a major movie studio that they were using CloudStack. They were using it to transcode video, and I thought that was terribly fascinating. What I found more fascinating is what they did during lunch, where they would spin up 50 or 60 game servers, and then as soon as lunch was over, they would destroy all the instances and go back to doing real work.
CloudStack is vast. It touches so many different aspects, and there's no one person that's kind of like a master of all those realms.
I think CloudStack as a project is going to be one of the leaders, simply because it's some of the most featureful and and robust platforms out there.
I don't see any limits to the cloud stack.